problem, no matter what that complicated piecewise description of curve is, it's this one. You go around half of the circle, and if you go through the second part, realize that is all in real line and starting from pi and ending up at in here. And because it's a parameterization independence, you remember that part? This complex integration is a parameterization independence. Once you look at separate this one, because it's kind of piecewise, you want to integrate this one using one parameterization, and you want to integrate this one that, throw away the complicated parameterization, replace it with a simple parameterization. As long as it's the same curve, the parameterization independence applies, and that's going to be the same value. Does that make sense? Right. So what is the simplest parameterization? And we're going to look at here. So let's see. That we'll do that later. But what we have in here is this perfectly closed circle with two singularities. And remember that when you're doing that z to the fourth plus 1, you have 4 singularities around the entire circle. You cut it in half. We only have 2 singularities. This time is not going to be 0. Right? So we have that. Let me do this slowly. So the first one here is e to the pi I over 4, and z1 is to 3 pi over 4. And then there are 2 more in the lower half plane, but we don't care about that. So here's the integral. That picks up the residue that is inside the loop, right? So not all 4 of them, but just the 2 of them, 0 and 1. Correct? Okay. So here's the residue at those 2 points. And how do we calculate the residue? I'm missing 2 pi I and sticking in here. It's that you multiply that residue, z minus zk. That's a simple pole, right? I think we noticed that last time. So you multiply that. By doing that, you're going to get rid of that factor from the z to the fourth plus 1. That simple 0 in there. And we use L'Hopital's rule. So it's, if you differentiate here, is 1. Denominator is 4 times z to the third. And then you stick it in on z to the zk. There's just something wrong. I deleted it and forgot to shift it over. Make sense? So if you stick it in there, then it's just simply 4 times z to the k the third power. And you can actually look at this expression and stick it in there and calculate the third derivative and so on. But I realized that z to the fourth is negative 1. Remember, we calculated all from here. Z to the fourth is z to the kth raised to the fourth power is negative 1. So I realize that because the zeros here, realize that simplifies a lot. If you use that trick, if you multiply zk and zk there, that picks up zk to the fourth power, right? So that becomes negative 1. Z to the fourth, and we have zk up there. So that becomes negative 1. So I pulled out negative outside and just calculating zk. And here's zk, and you actually look at these are 45 degrees, so we have root 2 and all that. So if you plug it in there, calculating this one is fairly simple. So it's root 2 over 2 pi. Yeah, up to here was this part. You'll get to that part? Yeah. And then if you use Mathematica from here, then you can easily check that it's root 2 over 2 pi. We're going to do one more example of this. This calculation is so tedious, and at some point, and it's even difficult to pull out this kind of trick and then do the rest of the part. But we'll do it symbolically and leave the detailed calculation to Mathematica. So here's an example. This example is non-simple pole. That's the one. So here's the integral c is z squared plus 1 squared, z squared plus 2z plus 2, and the numerator we have this thing, right? And then we have the circle c, not the full circle, but just like before, here's the circle. This r is big enough so that it contains all the poles that is involved in here. That's the situation in here. So I wrote down everything. So I wrote down if r is, I looked at this pole that is involved in here, realized that if r is greater than or equal to 2, all the poles in the upper half plane is going to be inside this loop C. So that's what we're going to do. All right? Make sense? Problem? And we want to pick out all the poles in upper half plane, because this is in the real line, like that. This is analytic divided by analytic, right? All the poles are coming from the things that are making the denominator zeros. So we're looking at z squared plus 1 squared in there. So what kind of poles do you see in there? It's fairly easy to calculate. Z equals plus minus I in there. I think someone would do that. Simple pole or not? Orders 1 or 2 here. Now this is z squared plus 1 will factor z plus I and z minus I, right? That's where the poles are coming from. But this entire thing is raised to second power, right? So therefore its order is 2. Not simple pole, right? What is different about this non-simple pole is that I realized that I forgot to introduce this one, but I'm gonna do that here. That's why I need to review that. We only looked at the method of calculating residue of a simple pole, right? So that's why it's slightly different. But what about this one? Z squared plus 2z plus 2. How are you going to factor this one? You complete the square, or you can use quadratic formula. But if you complete the square, it's going to be like this, I think. Agree? 2z plus 1 becomes 2. Okay, you complete the square, and then you do the same factorization, z plus 1 plus I and minus I. Here's a plus I, is minus I. From there we have z equals negative 1, negative I, z equals positive 1, negative 1, positive I, right? Make sense? If you set these, each of the factor equal to 0. This time his orders are 1, right? There's no higher power appearing here. So it's order 1. So that corresponds to simple poles. Okay? So for the sake of the time, I'm just going to give you a formula for how to calculate the residue when it is not a simple pole. So here is a review of a residue of A of f of z when the simple pole case. If f of z you're looking at it here and you're calculating the residue and it's if it's a simple pole, how do you do that? We multiply by z minus a, right? And then you take what operator here? Limit operator, right? But when you're actually calculating it, you use L'Hopital's rule, and that's a convenient tool. But this is how you formulate it. You multiply 1 power of z minus a, then that's going to shift that fractional part into a constant part of the analytic. And that, if you plug in, so that's how you do it. If it is not simple pole, so it's otherwise, it's slightly different. But it's not hard to see. If you look at Laurent expansion of the simple pole, and you have to shift it into analytic part, and then you have to pick up the right one. So first part is this. By multiplying f of z by what power of what so that it becomes analytic. If it's a simple pole of order n, right? This otherwise means it's a pole of order n. What is the lowest power then? Z minus a to raise the nth power in the denominator. Isn't that the pole situation? If you go forever, it's an essential singularity. So if I multiply by 1 in here, everything is going to be analytic. There's no fractional part. What is the power here of multiply? Nth power? Does that make sense? Yeah. Well, what is that you have to multiply? The denominator, right? In the Laurent series. What's the denominator in the Laurent series? Z minus a. So I want you to picture that Laurent expansion. If you multiply everything by z minus a to the nth, everything is going to cancel and become all polynomial terms. Is that right? Yeah. Now think about where the b negative 1, original b negative 1 is located. That's definitely not the constant part, right? The constant part is now b negative n. So it's somewhere down there. There's b minus 1 shifted all the way there, right? How are we going to pick that up? It is the Taylor series idea, right? So I'm just going to give you the answer, but you can easily verify it. You have to differentiate that Taylor series. One time you differentiate, you knock down one term, right? Constant term. If you do differential one more time, you're going to knock down A1. If you differential one more time, you're going to knock down. You can keep stripping off and disappearing, right? To get to that b negative 1, you have to differentiate it n minus 1 times. You just have to look at the term and calculate it to understand why it's n minus 1. All right? You got to that? But as you differentiate it, this n comes down and n minus 1 comes down and n minus 2 comes down. There's an additional coefficient there. What is that? N minus 1 factorial. So you have to divide it by n minus 1 factorial. Okay? I thought about all these last night, so it's still in my mind that I could just say these things, but I understand that it's not easy to understand. I just have to rush a little bit to, but that's the formula. If n is 1, then it's going to be this simple pole case, right? N is 1 and n equals 1, and n minus 1 says a 0 derivative. It means don't differentiate. And here's a, n equals 1, 0 factorial. So you're going back to that exactly, fc minus c minus a, right? But this is how you pick up the pole. As you can see that if this one here is not simple pole or pole of order 3 or 4, this could be really pain, and there's no good way to actually shortcut to calculate this one in general. All right. So that's the situation. Then what we want to do here is that we're going to write down the residue theorem 2, right? That's what the residue theorem 2 is about. So I'm going to write down like this of C, whatever that whole complicated thing. Is that all right? The whole quotient expression is about 2 pi I how many zeros do you see here? How many poles do you see? I don't think the 4 is the answer, because there's negative I, it's outside our loop, right? But I is up there, and it's going to be big enough so that it includes everything up there in upper half plane. What about this one in here? Negative 1 is this side, positive I is up there, right? But negative I is down there, it's not. So there are only 2 poles inside our loop, correct? So I'm going to put 2 in there. So residue of AK, those are the 2 values of this whole thing, where A1 is I, A2 is negative 1 plus I. Is that right? That's the situation. Right, let's calculate residue I of that expression. All right, is I simple pole or not? I think I'm still showing that. It's not simple pole. It's a pole of order 2, right? So how do you calculate the residue? This is a formula. If you want to calculate the residue, you got to multiply the right power and differentiate right amount, and this in this thing, all right? So I'm going to write that down because this order involved in here is 2. Pole of order 2. Here I see 1 factorial. You see that from the formula? 1 factorial. How many times are we differentiating? Just 1 time, order to 1 time. So just DZZ, right? And then we have this fraction quotient appearing in here. We're multiplying by what power? Z minus I to the second power, right? Okay, so here it is. If you look at that expression, there is Z squared, and there is Z squared plus 2Z plus 1 there. 2, I'm sorry. Then there was a Z plus 1. Let me write it down here. Z plus 1I, Z minus 1I, they're all squared. That's Z plus Z squared plus I squared, right? Completely factored. Is that right? Now we're knocking this one down as we multiply the second power of Z minus I in the formula here, right? So what's going to remain in here? z plus I squared. So if you multiply that appropriate amount, that's going to knock that down. This one is good. There's no singularity at I in here, right? Now you have to differentiate this one. And that's, you can see, everybody hates quotient rule in here. That's something, the tedious thing you have to go through. After you differentiate, one time you plug in what? I forgot to specify. After you differentiate, and what do we plug in here? The pole, and then there. So here we're going to plug in an I. Right? It's just like limit z approaching that pole. This kind of limit is here, right? But I describe it as a z plus. I think it's limit would be a correct thing. So that's, well, anyway, that you can, well, if I'm teaching calculus 1 and then asking that, now you can just picture this quotient rule applied it here and plug it in there, and they hated it. But you can, you're more than that. So you can picture that you can do this, right? So now I'm just going to copy the answer. And it turns out, if you do this calculation, is 9I minus 12 divided by 100. Right? So that's the fact. All right. The other one, two residues are there, right? Two residue. What is the other one? This one is a simple pole residue, right? So let's see. Here is that thing, and we're multiplying. We already factored it here. Which one is going to cancel as we multiply this z minus thing? Z is approaching, what is our pole? This is our pole, right? Upper half plane. So it's going to go -1 plus I. Now z squared is up there. Now it's not going to touch this guy, z squared plus 1 squared, right? There's nothing making that one 0 at -I plus I. So this part in here, there are two factors. One of them is here and the other one is there. One of them will cancel, right? Which one cancels? Which one disappears? First factor or second factor? Second factor, that corresponds to this one here, right? So second factor disappears, and z plus 1 plus I. As you plug in a -1 plus I, you're supposed to have non-zero number. If so, you've got to picked up the wrong factor, right? All right. Does that make sense? After you multiply that factor in here, that will knock down one power, and this is it. And if you plug it in there, another tedious calculation. But if you do that, what's that going to be? Is it 3 minus 4i divided by 25. All right. Modulo that hard tedious calculation, we have calculated all the residues here, right? Separately. So we're just going to go replace that with here it is. C star dz is a 2 pi I of residue at one of the pole in upper half plane. That's this guy, 12 by 100. What is the other one? Is a 3 minus 4i divided by 25. Okay? Then you have to calculate all that, and it's magically cancel the real part. Yeah, there's some factors in there. I think it's right. It's have factor of 4 in there. This, you can see the real part cancels, and imaginary part together with I leaves this interesting number 7 pi over 50. All right, we're going to come back to this result, pulling out some magic. So I'm just going to leave it there. Good. So going around that semicircle in upper half plane, the integral value is real number 7 pi over 50. So here's a example of a lot easier case. Let's try. I think, yep, that's the next one I need to do. It's exactly the same thing, a lot prettier than that. Here's r and -r. All right. This problem makes sense? We're integrating over 1 over z squared plus 1, And here is the same type of curve on the upper half plane. How many poles do you see in that upper half plane? This is really big. So for example, r is greater than 1. Only one, right? Only one, because z plus I and z minus I, only one kicks in there. Okay? So let's see. That is 2 pi I residue at where? I, and that's it. 1 over z squared plus 1. Isn't that right? That's it. There's only one pole in there. That's the residue theorem. So who wants to go for the residue here? 2 pi I. Simple pole or not? Is it z squared plus 1? Is it a simple pole or not? Yes, it's a simple pole. You factored it. There's no square, right? So what is that you have to multiply? The factor z plus I and z minus I, no other higher power appears. You got to multiply that one, right? So what survives in the denominator? Z plus I, and what are we plugging in here? Z equals I, the pole. Is limit z approach that pole. So what do you see in the denominator? 2i, right? So they cancel, it becomes pi. Another real numbers. Alright? But if you look at this one as like, ignore all these complicated integrals that you've been doing this for the half of the semester, if you turn this one into a real integral, what happens? Integral of 1 over x squared plus 1. You remember that definite integral result? So here's a little bit of pretend motivation. If you go from 0, negative infinity to positive infinity, 1 over x squared plus 1 dx. Anybody remember this result? Arctan is the antiderivative of this guy, right? And arctan of infinity, and remember arctan of infinity? It's pi over 2, right? If 90-degree tangent becomes almost infinity, right? So that picks up pi over 2. Minus negative infinity picks up negative pi over 2. So it's pi. If you look at the integral of that part here, that's what just happened. Isn't that real integral that involved in here, right? That value is the same as this entire integral. Interesting. But this is a finite integral. But if they go further and further, and that becomes this integral. But as we stretch it further and further, this integral around the complex value, does that change or not? Cauchy-Kosáth theorem. It doesn't change. It's always a constant, right? Always a constant. But if you divide into two pieces, those two pieces changes, right? But they always cancel, become one constant, right? So what they do is that they split this integral to complex upper half plane integral plus the bottom part, and kind of get a result of this one. And this is the magic. Okay? So here's the theorem. The analysis the book introduced about this part is something we've been doing a lot, so I'm just going to state it. There's no new technique to get this result. So here's the result. If you are going around the C0, I'm using the C0 notation for only the upper half piece, not the bottom piece in there. That's what C0 is, okay? And if you have a polynomial PZ divided by QZ dz, where this polynomial is actually, this result is for all complex coefficients, but this is only applied in here for real coefficients. This one approaches 0 as z approaches, not z, as we increase the size of this circle, which is controlled by the radius r, it's infinity. What you do is you just put an absolute value and pass it to the what is it? Parameterization formula and play with the absolute value. I wrote down in my note a neat proof of that, so I'm going to share that instead of you looking at the book. I think it's a lot easier to understand mine since you've been listening to my style of lecture. So I'll just share that at saving time. But that's the situation. All right, so let's write that down. What we have so far is I'm gonna call that bottom line here the gamma. That's all right. Okay. So the original integral, which is semicircle integral, is split it into a big loop up there and plus long gamma down there, right? And this one is always what value? What is the value of this integral altogether? It's just a pi in here. That's the residue altogether is simply just a pi. Remember? We did the residue calculation. If you go around, it's just a pi, right? So next part is that what we want to calculate is just this gamma part, right? So gamma part is a pi minus the whole upper loop part. Now you're taking the limit, then it becomes limit r approaches infinity, right? Of that gamma is equal to pi minus what happened to this part, upper circle. It became 0, and that's the result. In this part, sorry about this, I forgot to make a connection here. Does it look like this situation, p divided by z, these are the polynomial? It looked like that, and I even forgot to put down some condition in there. Sorry about this. Degree of q and degree of p must be at least 2 difference. Sorry about this mess. So here's the degree of numerator is what? 0, right? Degree of the denominator is 2. So if you look at all the big circles, this degree, large enough degree, really dominates, really making it 0. This rough discussion of why this one becomes 0. Okay? So we have that, therefore, this part in here, upper half part, is becoming 0. So that we have this result. All we have to now is that come up with a nice parameterization of gamma and turn that into a parametric parameterized integral form, not the contour integral form. All right? So what is a good parameterization of gamma? If you're looking at this picture here, and this bottom line is all in the real line, right? Isn't that just t plus 0 times I, where t is varying from negative r to positive r, which even respects the orientation of a bottom line? What do you say? Good? Yeah. Now we have to enter this gamma part of this 1 over z squared plus 1 dz. Now let's enter the parameterized version. So what is the t value varying here? T from where to where? Negative r to positive r. It's a bottom line in here. 0 to pi was upper part. And then you actually have to do that when you show this approaching 0 part. But right now we're looking at the bottom. It's negative r to positive r. Is that right? Then you replace this one with this, what z is. Now z is just a real number, so it's a t squared plus 1. Right? You multiply by what? dz dt. dz dt, right? So what is dz dt here? Here's the formula, z equals t plus 0i. You differentiate that, becomes 1, right? The other one is just a 0. So isn't that just 1? So it becomes negative r to positive r and t squared plus 1 and t dt. We're back to Calc 2. This one right here, right? And then as this r approaches infinity, what happened to this value? This value approaches pi in there, right? This is pi. Interesting. Yeah. So let me go back to that example and pull up another magic there. In the homework, you calculated this guy, z to the 4th plus 1 dz. over c, and we have c going around like this, that we have c0 and we have gamma there. How many poles were there for this example? Remember that part? There were two, right? There was one, there's another one there. There were 2 poles. And we calculated that. And this thing, c going around all the way over a closed circle, is, what was the value? I think the value was, so we're back, and here it's root 2 over 2 pi. Good? So let's split this one again. So we have root 2 over 2 pi is equal to integral over the upper circle, c0, plus the bottom real part. Alright? So if you're interested in the bottom real part, is root 2 over 2 pi minus upper circle, right? But if you look at this as a polynomial divided by polynomial, do you recognize this degree is more than 2 different? Numerator degree is degree 0. Denominator degree here is 4. So this degree is big enough, the difference is big enough, so that this one approaches 0, right? So that one approaches what number now? Root 2 over 2 pi is a constant, and this one becomes 0 because of that earlier result I showed. So let's write that down. The same phenomenon. If you replace this one with a real parameterization, negative r to positive r, it becomes the same thing. So here we have the result. It says negative infinity to positive infinity over 1 over t to the 4th plus 1 dt is supposed to be what number now? The root 2 over 2 pi. That was the answer. Okay, so if you go ahead and type in Mathematica, you can type in a capital in negative I infinity, I in capital. It'll calculate this thing symbolically, and then it'll give you this result and verify that. But often we only care about, hey, this is symmetric, even function around t equals 0. So from 0 to infinity, what would you say about this one? Half of it, right? Half of it. So 0 to 4 pi. Okay? So when you go back in here, where is that guy? The ugly one. It was there somewhere here. All right. Here. Remember that polynomial here? These are all real coefficient, right? So this has a complex 0. That has also complex 0. There's no singularity along the way of real line. So if you put around this circle in here, and you calculate this one, and the answer was 7 pi over 50. Okay? But what happened? What is the degree in here? Degree 2 there, right? Is it degree 2? Oh, it's not showing the right thing. And what is the degree down there? Degree 2 and degree 4, right? So the difference is at least 2. So still the upper circle is going to approach 0. From all that, we have a result. It says, from recall the earlier example, then we have negative infinity to positive infinity of t squared plus 1 raised to square power t squared plus 2t plus 2, and in the numerator t squared dt. But remember the answer was 7 pi divided by 50. So you can plug it into a Mathematica and see what happens there. They also introduce different samples of these examples, and once you understand this idea of separating, where's the first time I'm introducing this idea is this one here. Upper half approaches 0 and the bottom becomes the main portion of this integral value. It gives you an application to that the real integral, definite integral problem, right? And they introduce a couple more of these examples in the book. So I'm going to leave that for you to read that part, but I'm going to end this one briefly with one extra calculation with this one is a real good one. Since I don't have only about 10 minutes, I'm just going to pretty much summarize this result rather than actually going through the calculation. But I'm going to post a detailed calculation and take a look at that if you really like this last result we're about to go through. Okay? All right. Here we go. Again,